Hello viewers! I recently released a video about acids and bases, and I'm sure at least one of us has become curious about the strengths of different acids and bases. So let's find out. This is the pH scale. It goes from 0 to 14 and it shows pretty much all the acids and bases you would ever need. However, there are needs to extend this scale later. First, let us define pH. pH equals negative log 10 concentration of hydrogen ion. For example, pH of hydrobromic acid is 1.08. That means that the concentration of hydrogen ions, actually that's just a proton, equals about 0.08 moles per liter, which means that 83.2% of the hydrogen ions will escape out of the molecules. If we work from the formula, we can see that as pH increases, there will be less free hydrogen ions, since acids work by releasing their hydrogen ions, and increasing pH leads to a worse acid. Well, why exactly should we use pH for bases? Don't they release hydroxide ions? They do, and we can still use pH to measure it. But first, an explanation of why the pH scale only goes up to 14. To do that, we need to make use of the special properties of water. Water is made up of one hydrogen ion and one hydroxide ion, so for every unit of H plus released, 1 unit of OH minus is released as well. So the pH of water is equal to the pOH of water, and pOH is just a mirror of pH. Now we measure it. The pH of water is 7. So pH plus pOH is 14. This makes sense since you can't get better at being acid and base at the same time. And since pOH only goes down to 0, pH goes up to 14 and vice versa. This means that to calculate the pH of sodium hydroxide, a very strong base, we also need to work out its pOH, and that's 0. So the pH of sodium hydroxide is 14 minus 0 equals 14. That being said, let's plot it on the table. Now is the time to rally off all 19 of common chemicals' pHs. Hydrochloric acid, pH 1, nitric acid, pH 1, perchloric acid 1, sulfuric acid 1, phosphoric acid 1.6, hydrofluoric acid 2.1, formic acid 2.4, benzoic acid 2.8, ethanoic acid 2.9, carbonic acid 3.9, water and salt water all at 7, pyridine 8.8, ammonia 11.1, methylamine 11.6, sodium hydroxide 13, potassium hydroxide 13, lithium and barium hydroxide also at 13. Then how do we measure pH? We use a special glass bowl. After coating it with some magical gel, not really, and sodium ions and filling it with acid, we drench it in the stuff we're trying to measure the pH of and read the resulting electricity charge. Time to up the ante. There are a lot of ties around the scale. For example, sodium hydroxide and barium hydroxide, which are both at 13. So now we require a tiebreaker, and that is pKa. pKa is defined as this. Okay. At this level, we have the second tier of acids and bases. On the left side, extremely strong acids take the stage. Battling for bottom pKa, they are trifluoroacetic acid, negative 0.3, nitric acid, negative 1.4, methane sulfonic acid, negative 1.9, sulfuric acid, negative 3, hydrochloric acid, negative 6, hydrobromic acid, negative 9, hydroiodic acid, negative 9.3, perchloric acid, negative 10, triflic acid, or full name, trifluoromethane sulfonic acid, negative 14, fluorosulfuric acid, negative 50. And that is 1 trillion times more powerful than sulfuric acid. And on the right side of the scale, the extremely strong bases contend for top pKa. Sodium hydroxide, 15.7, tert butoxide, 18, Acetylide 25, hydride ion 35, potassium amide 38, which is a quadrillion times worse than sodium hydroxide. Ooh, okay, this is pretty bad. Now that we've finished up the pKa scale, it's time to expand the scale again. With this, we enter the region of the Hammett acidity scale and proton affinity. The less the H0 or Hammett acidity scale reading, the stronger the acid. The greater the proton affinity, the stronger the base. We have to use H0, which is the Hammett acidity scale, and proton affinity. I'll call these chemicals tier 3. Let's get this over with. Perchloric acid, -13. Trifluoromethane sulfonic acid, -15. Chlorinated carborane acid, which is essentially a huge ball, -18. Very amusing structure. Magic acid, -27. And fluoroantimonic acid, -31. Alright, and bases. Cesium hydroxide, 1630 kilojoules per mole. Sodium hydride, 1675 kilojoules per mole. Sodium amide, 1680 kilojoules per mole. And Schlosser's base, a mixture, which is 1800 kilojoules per mole. And that's the last one I actually got by my research, but N-butylpotassium at proton affinity 1845 kilojoules per mole, which is actually quite large. And that's really about as high as we can go.